If you subscribe to my channel, Chemistry Lessons, here we go. So hopefully you've already subscribed. If not, please do. It's right down there, look. Somewhere on the screen anyway, there's a subscribe button. If you already do, then let your friends know. It's the best and coolest place to learn some chemistry. This channel predominantly focuses on AQA A Level at the moment, and the lessons that are on there at the moment are designed to be full lessons. Ideally, in the future, I'm looking at going to put together some short, snappy revision videos that will focus on key concepts, so look out for those. So this video then, it is in fact an AQA A Level. There are other videos out there on BTEC Applied Science. This video is a second year topic. It's spec point 3.1, which means it's physical chemistry, and it's the 10th topic. It's KP. Okay, it's to do with an equilibrium constant. You may recall in first year that you studied the Kc equilibrium constant, but this is a Kp. Very, very similar. So, because it's so similar, in fact, let's have a recap of something from Kc. So perhaps you want to pause the video and see if you can work this out for yourself, but we've got some information here. And you've been asked to deduce the moles of nitrogen and ammonia at equilibrium. So you may wish to pause now. Okay, so what we do is I always suggest that you work in columns directly underneath the equation. And we've got a column for the H2, we've got a column for the N2, and we've got a column for the NH3. We will have some information at the start. We'll have some sort of change will take place, and then we'll have the amount at equilibrium, and we deal in moles. This is like a mole table. So we're told that 3.2 moles of nitrogen, so at the start we have 3.2 moles of nitrogen, they're mixed with 2.8 moles of hydrogen, and therefore we assume that there is no ammonia at the beginning because we've added those two together. And then it says at equilibrium 0.7 moles of hydrogen remains. So that's the information I'm taking from the question. I'm completing my table with information that I've been given. So where do we go next? Well, I can work out the change here. I can see that this has gone down by 2.1 moles. That means that this will also go down. It's like a seesaw, it's equilibrium. If the reactants are going down, the products are going up. So both reactants must be going down, but they'll go down in ratio. So this will go down, the nitrogen will go down by 1/3 of what the nitrogen went down, because we have to divide by 3 across here. So this will go down by 0.7 due to the 1:3 ratio. So I've taken 2.1 and I've divided it by 3, and that's shown that this will go down by 0.17. And I can find out my moles then. So 3.2 take away 0.7 would have an equilibrium moles of N2 as 2.5. So I've calculated my moles of nitrogen. I now need to calculate the moles of NH3. So this will increase this time, and it will increase by 2.1 divided by 3 times by 2. The ratio is 3 to 2, so this will go up by 1.4. which means we'll have 1.4 moles of ammonia at equilibrium since it started at 0. This is going to come in very useful as part of KP, because this is something we're going to have to do here as well. Let's look at the specification then for KP. So equilibrium constant KP is deduced from the equation, just like Kc was, and we'll remind ourselves of how we did that for Kc. And we're going to look at it, how we calculate this from something called partial pressures, and we'll see something down here called a mole fraction. Okay, so we're actually going to start, and I'm going to look at these first 2 bullet points here. Okay, but first off, I'm going to remind us of what Kc was. So Kc we derived directly from the balance symbol equation. So if we had a chemical reaction where we had A plus 2B equilibrium C plus 3D, our equilibrium constant Kc would be equal to the concentration of D to the power of 3 multiplied by the concentration of C to the power of 1 divided by concentration of A multiplied by the concentration of B to the power of 2. That was derived directly from the equation. The square brackets were essential when we did Kc because it represents concentration in moles per decimeters cubed. This 3 from here, the 1 and the 1 here, and the squared from here. Okay, and Kp is very similar. Okay, the big difference with Kc and Kp is Kc deals with concentrations in moles per decimeters cubed, where Kp is for a gaseous equilibrium, so it's for a gaseous system. You can use Kc for a gaseous system as long as you calculated concentrations, but Kp uses gases and partial pressures and mole fractions, and we'll see that on the next slide. Okay, so in order to determine a Kp, the equilibrium would need to be in gaseous state. I'm going to change my general equation just a little bit so it can vary. Must be an equilibrium though, kind of makes sense. And they're all in gaseous state. Okay, so my expression for Kp then, in a similar fashion to Kc, it's C to the power of 1 multiplied by D to the power of 1, but this time, instead of being concentrations, we call it partial pressure. And we can put that in regular brackets. Do not put them in square brackets. Do not use square brackets for Kp. And then it would be partial pressure of A squared multiplied by the partial pressure of B to the power of 1. So Kp is deduced from the balanced equation, but we do not use square brackets, we use curly brackets, and it's partial pressures. The Pp you can just get away with a single P. Sometimes you see P, sometimes you see inside the brackets, sometimes you see outside the brackets. But the important thing is do not use square brackets here. Okay. Now, what in fact is PP? What is partial pressure? Okay. Well, the theory is that at equilibrium there will be a total pressure. There is always going to be a total pressure, and pressure is, if you do physics or GCSE physics even, pressure is due to the gas particles hitting the sides of the container. Okay. Now there are several things that will affect the pressure, but ultimately what we're looking at is that the pressure is due to all of these substances. The pressure is due to A, B, C and D. Okay. So that means that each one of those contributes slightly differently to the total pressure. The total pressure is made up of all of the partial pressures. So the total pressure, and I'm going to make a little note of that, the total pressure is in fact the partial pressure of A and the partial pressure of B and the partial pressure of C and the partial pressure of D. It's the partial pressures. The sum of all the partial pressures will equal the total pressure. Okay. Now, in order to determine the partial pressure, if we want to find out the partial pressure, we need to know how many moles we've got. Okay. So the partial pressure is the mole fraction multiplied by the total pressure. In other words, the partial pressure of A is its mole fraction multiplied by the total pressure. So the sum of all the partial pressures will add up to the total pressure. Let's see an example of how we'd work out a mole fraction then. So just as before, you would work out, and we won't do it here, but let's just assume we've worked out our little table and we've got our moles at equilibrium of A, B, C and D. So I'm going to say that I've done all that working out and I've got my mole fraction sorry, not my mole fraction, I've got my number of moles of A as 2. And I've got my number of moles of B as 1. And my moles of C is 3, and my moles of D is 1. So I'm just making this up here, but those are my moles at equilibrium, and we would work that out the exact same way as we work out the moles of equilibrium when we do Kc. We'll get to do some practice in exam questions in a couple of slides time. So to work out the mole fraction then, so I'm trying to work out the mole fraction, it's this total moles, so the total moles, I'm going to find the total moles here, 2 plus 1 is 3, plus 3 is 6, plus 1 is 7. So the total moles is 7. So to work out the mole fraction is the moles divided by the total moles. The moles divided by the total moles. And the moles divided by the total moles. Moles divided by the total moles. That's the mole fraction. And if you add all the mole fractions together, you should end up with 1. So the sum of the mole fractions is equal to 1. And the sum of the partial pressures is equal to the total pressure. So you've basically worked out a fraction of the moles, the mole fraction. What is that moles as a fraction of all of the moles? Total moles is 7, so you just divide the number of moles by the total moles. That gives you the mole fraction. To then calculate the partial pressure, you calculate your mole fraction by the total pressure. So there's quite a lot going on here. There's a few new terms. And as you could imagine, when it gets to the exam, there's several different ways, because there's so many kind of different values here, if you like. There's so many ways that the exam questions can ask you here. They could give you a total pressure. The standard way would be they'd give you a total pressure and you would have to work out partial pressures, or they could give you everything but one mole fraction and you have to determine what that is. So there's all sorts of different questions you can expect, and we'll look at a couple here. And as with physical chemistry, the more you practice, the easier it becomes, okay? Physical chemistry is all about practicing application. Okay, now we've done the deriving the partial pressure and mole fraction and total pressure. Constructing the expression, yes, we've done that. That's very similar to Kc, but remember, do not use your square brackets. Performing calculations, well, we just need to do some practice of those, and we've got some questions coming up, okay? And the section down the bottom here, where it talks about predict the qualitative effects of change in temperature and pressure on the positions of equilibrium, this is just year 1 Le Chatelier, okay? But we'll look at those, we'll remind ourselves of what that is. And therefore, what you then do is you use those to make predictions on how Kp will change. And again, here I'm just going to remind you of Kc. A large Kc value meant that equilibrium was further to the right. A small Kc value meant equilibrium lies to the left. And the idea was anything below 1, it's to the left, and the smaller, the further left. Anything above 1 lies on the right, and the bigger the value, the further right it lies, okay? Right, and the very last bullet point, understanding whilst the catalyst can affect the rate of attaining equilibrium, it does not affect the value of the equilibrium constant. Again, that comes straight from equilibrium in year 1 when you do Kc. Kc is only affected by temperature. Temperature is the only thing that affects Kc, and it's exactly the same with Kp, which is why we have to make predictions. So we're going to look at these 2 bullet points on the next slide, okay? Okay, so I'm going to make up, I'm fed up of using A's and B's, so I'm going to use some X and Y's. I'm going to use Z, I'm going to make 3Z. These are all going to be gases because we're going to be focusing on Kp, 2 there, and we'll have a 2 there. Don't even know what this is, but anyway, 2x plus 2y, equilibrium 3z. Now, this forwards reaction, I'm going to say that this is eeny, meeny, miny, mo. Let's go with an exothermic, minus 50 kilojoules per mole. So whenever you're given a delta H value, that is always for the forwards reaction. So the forwards reaction is exothermic. That means the backwards reaction would be endothermic. Now, let's look at the effects on pressure. So what happens if we change the pressure? If we increase the pressure, this is now revision of first year Le Chatelier. If you increase the pressure, it favours the sides with the fewest moles of gas. So if you increase the pressure, it shifts to the side with the fewest molecules of gas to oppose the change. Okay? So here, if we increase the pressure, equilibrium will shift to the right-hand side because there are fewer molecules of gas on the right, and equilibrium will shift to oppose the change. And the opposite will happen if I decrease the pressure. If you decrease the pressure, it favours the side with the most molecules of gas, which in this case would be to the left. So decreasing the pressure, equilibrium will shift to the left, and therefore to oppose the change, and you would have a larger proportion of X and Y than you did before. So equilibrium will shift to the left if you decrease the pressure. However, Kp does not change. So when equilibrium shifts to oppose pressure, Kp will not change, just like Kc did not change when you changed the concentrations. The only time Kc changed is when we changed the temperature, and that is also correct with Kp. Now, if you increase the temperature, equilibrium will shift to oppose the change, and the easiest way to work this out would be to write the word temperature in your equation, and I'm going to say that the forwards reaction is exothermic, so heat is on the right hand side, heat in the exothermic direction. If you increase the temperature, equilibrium will shift to the endothermic side, which is in this case to the left. So increasing the temperature, equilibrium will shift to the left to oppose the change, and therefore decreasing Kp. Need to go back to green. Can't do that in red, can I? So if you increase the temperature, equilibrium is going to shift to the left, and that's even the wrong shade of green. This is great. So if you decrease the temperature, equilibrium will shift to oppose the change, which is the endothermic side, which in this case is to the left, which means in this case, Kp will decrease. Okay? So you need to appreciate that if equilibrium shifts left, Kp decreases. If equilibrium shifts right, Kp increases. So all we're doing here is applying Le Chatelier, and then we're going a step further and explaining what will happen to Kp. We're saying Kp will increase or Kp will decrease. So if we were to decrease the temperature here, decreasing the temperature, equilibrium will shift to the exothermic side to oppose the change, which in this case, if we decrease the temperature, it will shift to the exothermic side, which is to the right. So a decrease in temperature in this case would cause an increase in Kp. Because equilibrium shifting to the right, we've got more products to reactant ratio. If you've got more product to reactant ratio, Kp is bigger. Okay? And if we decrease the yield of Z, if equilibrium shifts to the left, you're going to have a smaller Kp. So we're combining our understanding of Le Chatelier and application of Le Chatelier from first year, and we're using that to go one step further and predict what will happen to Kp. Not quantitatively, just qualitatively. We're just verbalizing it will go up or down. Okay? Now, you might be thinking, but how come it doesn't affect with pressure? Okay? Now, we don't really need to know that, but I'm very happy to explain it should people ask about it. So if you really want to know, you don't need to, but you should just know that Kp doesn't change with pressure. It only changes with temperature. Okay, so looking back at the spec there, we've covered all of these new terms and the new points. The big thing here really is lots and lots and lots of practice questions with Kp. Okay, you will find that as a lot of physical chemistry, the more past questions you can do, the better you get at it, because they do get repetitive. The bulk, the majority of the marks get very repetitive. So practice, 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 exam questions for Kp. Okay, you know the drill by now. So first couple of questions we'll start off with is multiple choice. So pause the video and when you're ready, unpause and we'll go through them. Question 1 then, equilibrium mixture is prepared. There we go, we've got a delta H, so the forwards reaction is exothermic. And the temperature of the mixture is decreased and the mixture is allowed to reach equilibrium. So if we decrease the temperature then, let's try and get a head start and see which way equilibrium is going to go. If we decrease the temperature, equilibrium will shift to the right and therefore this will increase and these two will decrease. Right, okay. So the mole fraction of carbon monoxide, that will decrease, so no, it won't be greater. So which is greater? The mole fraction of carbon monoxide will definitely not be greater, it will be smaller. And also the partial pressure of chlorine, because there'll be less moles, will have a smaller partial pressure. The total pressure, I would imagine here, you might be uncertain, but I would imagine the pressure would decrease because you're decreasing the temperature. It certainly won't increase, okay? So I think it's not C, so hopefully its elimination is D. The value for Kp, well yes, Kp will change with temperature. Temperature is the only thing that will affect Kp and Kc. Since equilibrium shifts to the right, Kp increases. Yes, the answer is D. Question number 2. Which statement about Kp is correct for this reaction? Delta H is, again, it's exothermic. So what's happening here? Kp is independent of the pressure. So that means that Kp does not depend on pressure, and that's correct. Pressure will not change Kp. So I'm tending to agree with this one already, but we might as well eliminate the rest because Kp is dependent on temperature, but it's independent on pressure. So I think that's true. The Kp increases as pressure increases. No, it doesn't, because pressure can't affect Kp. The value of Kp increases as temperature increases. Well, it could, but let's check. If you increase the temperature, equilibrium will shift left and Kp would decrease. So that's a sneaky one, that, because Kp would actually decrease. The value for Kp is independent of temperature. No, it's not. It is dependent of temperature. So yes, the answer here is A. A pretty lengthy question here. Okay, there's a lot going on. It's a calculation. So take your time. My advice before you start is to do yourself one of those mole tables because you will need it. Take a good 10 minutes and when you're ready, unpause. Right, okay, so my advice always is to have your little mole table. Makes it much more logical and clear to set out. So I'm going to have 3 columns because I've got 3 substances. I've got and it's moles we're dealing with here. It's going to be moles. And we've got the start. And we're going to have change. See, I haven't even read the question yet. Change, and then we've got equilibrium. And then when it's a pressure one, we want to have a mole fraction. And then possibly a partial pressure. We'll see how far we need to go. So 62.8 mole sample of carbon monoxide. So the start, we've got 62.8. Was added to 146 moles of hydrogen. When equilibrium was reached, the mixture contained 26.2 moles of methanol. So we had 0 at the start. That means that the methanol has gone up by 26.2. So my advice now is, let's see what we're actually asked to calculate. But this is going up by 26.2. So we're being asked to have an expression for Kp and calculate a value for Kp. Okay, or Kp. Sorry. Right, so methanol has increased by 26.2. That means that this would have gone down by 26.2. And this would go down by 2 times 26.2. So when you do this change, we take into account the molar ratios because the CO and the CH3OH are 1 to 1, so they will increase and decrease by the same amount. However, the hydrogen, it's 2 to 1. This will change by twice as much. Okay. Then what we need to do is work those out. I'll just get my fantastic device out that does calculations for me. I call it a calculator. I'm not sure what they call them in the real world. 62.8 take away 26.2 equals 36.6. And the next one, 146 minus 2 times 26.2 equals 93.6. Okay, so what I'm going to do is work out the total moles, which is all of those added together. So 36.6 plus 93.6, struggling with my calculator, plus 26.2 equals, so my total moles is 156.4. So I'm going to work out the mole fraction, which is basically the moles divided by the total moles. So 36.6 divided by 156.4 equals 0.234. Whee. And the next one, 93.6 divided by 156.4 equals 0.598. And finally, 26.2 divided by 156.4 equals 0.168. Okay, just double check, they should all add up to 1. They should all add up to 1. 0.234 plus 0.598 plus 0.168 should equal 1. Yes, it does. Then to work out my partial pressure, I multiply the mole fraction by the total pressure. Total pressure, 9.5 megapascals. So all I'm going to do, 0.234 times by 9.5 equals 2.223. And then 0.598 times by 9.5 equals 5.681. And finally, 0.168 times by 9.5 equals 1.596. Now when I add all of those together, I should get my total pressure, which is 9.5 megapascals. Notice the units here, by the way, megapascals. Okay, right, long-winded I said, right? It's 8 marks. So now I'm going to write my expression for Kp. My expression for Kp is equal to the partial pressure of CH3OH to the power of 1 divided by the partial pressure of CO to the power of 1 multiplied by the partial pressure of H2 squared. Okay, equals, well, let's get a numerical value there. I'm going to punch those in the calculator. I've got them down there. Look, 1.596 divided by 2.223 times by 5.681 squared. It's important how you work these out, because actually that bottom section there all needs to be in brackets before you divide. So be careful with your calculator. It's easy for people to make calculator errors here. And the answer comes out at 0.022. That's my numerical answer. So I've got 0.022. I haven't given the units, okay? Now the units, we need to work them out, because the units are going to be megapascals divided by megapascals times megapascals squared. So the bottom becomes megapascals cubed. So it's megapascals divided by megapascals cubed. So 1 minus 3 is minus 2. My units are megapascals to the minus 2. Okay, that's deducing units. You may need to do some work on that. If you want some help on deducing units, give me a shout and I can help out. Okay, last question then. You know the drill. 13 marks for grabs here, so pause the video, have a go at this question, and when you're ready, unpause and we'll go over it. Okay, so we've got an equilibrium at the top there, sulfur dioxide with oxygen making sulfur trioxide. You don't need to be familiar with the reaction. In fact, they're going to purposely make you unfamiliar with the reaction. Okay, so we've got an equilibrium at T1. We know the forward reaction is exothermic because we are told that delta H is minus 196, so we know the heat will be on the right hand side. We are told that the partial pressure for sulfur dioxide is 24 and the total pressure is 104. We also know that they are mixed in a 2-to-1 ratio, 2 to 1 as well, so it's 2 to 1. So therefore, if we know the partial pressure of sulfur dioxide was 24, the pressure for oxygen, because there's half as much, will be half as much. So the partial pressure for oxygen is 12 kilopascals. That's going to give us 1 mark. The mole fraction now. So if we remember, the partial pressure is equal to the mole fraction multiplied by the total pressure. So if we want to find the mole fraction, we can just divide the partial pressure by the total pressure. So if we do 12 divided by 104, that equals 0.115. That's all 3 marks. Okay. Calculate the partial pressure of sulfur trioxide. Well, again, what we know here is we know the sum of the partial pressures equals the total pressure. The total pressure is 104. We know the partial pressure for oxygen was 12 because we just calculated it, and we know the partial pressure for sulfur dioxide is 24, which leaves us with 68 kilopascals. That's why it's only worth 1 mark, a quick 1 mark there. Expression for Kp, I'm going to use the space over here for this. So Kp will be the partial pressure of SO3 to the power 2 divided by the partial pressure of SO2 squared multiplied by the partial pressure of O2. And the calculation, we'll just punch these into our calculator now because we've got the partial pressures 68, 12 and 24. We'll put those into our calculator and you should end up with 0.669, and we're asked for the units. Now to deduce the units, we've got kilopascals squared on the top. On the bottom we've got kilopascals and kilopascals squared. Okay, so on the bottom we've actually got kilopascals cubed because we've got pascals times pascals squared. And then to deduce, to work out the units, it's 2 minus 3, because it's indices, law of indices, divided by, so kilopascals squared, divided by kilopascals cubed. 2 take away 3 is minus 1. So my units are kilopascals to the minus 1. D. When equilibrium was established at a different temperature, T2, the value of Kp was found to have increased. Right, that's telling me the equilibrium has shifted right. That's telling me the equilibrium has shifted to the right. State which temperature was the lower temperature. Right, well, if we want it to shift to the right and the forwards reaction is exothermic, that means that we've decreased the temperature. So the lower temperature is the temperature where Kp was the biggest, which in this case is T2. So T2 is the lower temperature, and my explanation is using Le Chatelier that Kp has increased. That tells me that equilibrium has shifted to the right. Now equilibrium will shift to the right in the exothermic direction when the temperature has been decreased. Okay? And in part D, in a further experiment, the amounts of sulfur trioxide, oxygen and catalyst and temperature were all unchanged. This time we had a smaller volume. What that's telling me, a smaller volume, that's telling me that they've increased the pressure. Okay? Deduce the effect on the yield of sulfur trioxide. So if we increase the pressure, it will shift to the side with the fewest molecules of gas, which in this case is to the right. We've got 3 molecules of gas on the left and 2 molecules of gas on the right. 3, because you've got 2 sulfur dioxides on the left, 1 oxygen, so that's 3. On the right hand side, we've got 2 moles of SO3. So here, a decrease in pressure will shift equilibrium to the right, which will increase our yield on SO3. We've not been asked for an explanation here actually, but it's an increase. That's because it will shift to the side with the fewest molecules of gas, in this case is to the right. Now, Kp will remain unchanged because Kp will only be affected by temperature. So Kp is unaffected. Yes, the equilibrium has shifted, but Kp does not change. Kp will only change with temperature. So there's no effect on Kp for this one. And that's the end of this lesson then. So hopefully that was useful. And you know what? You know what you need to do. Thank you very much.